Hello? Today, we're going to dive into rational functions and a very important concept, end behavior. We'll focus on what happens to these functions as x gets really, really big, or really, really small. By the end of this video, you will be able to, first, you'll be able to define what a rational function is. Second, you'll learn how to use the leading terms to determine the function's end behavior. And third, you'll be able to identify and find asymptotes based on the degrees of the polynomials in the numerator and denominator. So, what is a rational function? Let's start with a formal definition. A rational function, which we can write as r of x, is simply the ratio of two polynomials, p of x and q of x. This is a key concept. A rational function is any function that can be expressed as a polynomial divided by another polynomial. Now, there's a crucial condition here. The polynomial in the denominator, q of x, cannot be equal to 0. Why? Because division by 0 is undefined. This means that for any value of x that makes the denominator 0, the function r of x is not defined. We'll explore this further when we talk about vertical asymptotes. A helpful way to think about a rational function is that it compares the relative size of its numerator and its denominator. Now let's talk about end behavior. In other words, what happens to the graph of r of x when x gets very large, either positive or negative? The end behavior of a rational function is entirely determined by its leading terms. Remember, a leading term is the term in a polynomial with the highest power. For instance, in the polynomial 3x cubed minus 2x plus 5, the leading term is 3x cubed because x cubed is the highest power. For very large absolute values of x, these leading terms become so much larger than all the other terms combined that we can essentially ignore the rest of the polynomial. They dominate the behavior of the entire function. So, to examine the end behavior of our rational function r of x, we just need to look at the quotient of the leading terms of p, of x and q of x. In this expression, a sub nx to the power of n is the leading term of the numerator polynomial p of x, and b sub mx to the power of m is the leading term of the denominator polynomial q of x. In other words, n is the degree of the numerator, and m is the degree of the denominator. This comparison of the degrees n and m is the key to understanding all the different types of end behavior. There are three main cases we need to consider when comparing the degrees of the numerator and denominator. We'll go through each of them. The first case is when the degree of the numerator, n, is less than the degree of the denominator, m. If n is less than m, the denominator grows faster than the numerator. Think about dividing a small number by a very, very large number. The result will get closer and closer to 0. Mathematically, we say the function's end behavior is that it approaches 0. This behavior results in a horizontal asymptote at the line y equals 0. An asymptote is a line that the function's graph approaches but never touches as it extends infinitely. So, for very large x, our function will look almost identical to the line y equals 0, the x-axis. Let's look at an example to solidify this first case. Consider the function f of x equals 4x over x squared minus 9. Our first step is to identify the degrees of the numerator and the denominator. The numerator, 4x, has a leading term of 4x to the power of 1, so its degree n is 1. The denominator, x squared minus 9, has a leading term of x squared, so its degree m is 2. Comparing them, we see that n is less than m. This fits our first case. We can predict that the end behavior will be that the function approaches 0, and there will be a horizontal asymptote at y equals 0. Let's verify this by looking at the graph. Notice how the graph gets closer and closer to the x-axis, which is the line y equals 0, as you move to the far left or the far right. This visually confirms our conclusion. Now let's explore the second case. This occurs when the degree of the numerator is equal to the degree of the denominator. So, n equals m. In this situation, the numerator and denominator grow at the same rate. This means their ratio won't shrink to 0 or grow to infinity. Instead, it will approach a constant value. The function's end behavior is that it approaches the ratio of its leading coefficients. The asymptote for this case is a horizontal asymptote located at y equals a sub n divided by b sub m. These are simply the numbers in front of the leading terms in the numerator and denominator. Let's work through an example for the second case. Consider g of x equals the quantity 2x squared plus x minus 1, divided by the quantity 3x squared plus 2. The numerator's degree n is 2, and the denominator's degree m is also 2, so n equals m. Because the degrees are equal, we know there will be a horizontal asymptote at the ratio of the leading coefficients. The leading coefficient of the numerator is 2, and the leading coefficient of the denominator is 3. So the horizontal asymptote is at y equals 2/3. Again, a quick look at the graph confirms this. As x moves away from the origin, the function's curve gets incredibly close to the horizontal line y equals 2/3. This constant value is its end behavior. Finally, let's examine our third and final case. This case is when the degree of the numerator, n, is greater than the degree of the denominator, m. Here, the numerator grows faster than the denominator. This means their ratio will increase without bound. In other words, the function approaches positive or negative infinity. The end behavior of the rational function will mimic the end behavior of the polynomial you would get if you performed polynomial long division. This is often called the polynomial quotient. This might result in a different type of asymptote. If the degree of the numerator is exactly 1 greater than the degree of the denominator, you will get a slant or oblique asymptote. This means that the end behavior of the function is the same as that of a line. We can find the equation of this line by performing polynomial long division. Let's demonstrate this third case with an example that has a slant asymptote. We'll analyze h of x equals the quantity 2x squared plus 5x plus 1 divided by x plus 2. The numerator's degree n is 2. The denominator's degree m is 1. We see that n is greater than m, so we're in our third case. Specifically, because the degrees differ by exactly 1, 2 minus 1 equals 1, we expect to find a slant asymptote. To find the equation of this line, we use polynomial long division. We divide the numerator polynomial 2x squared plus 5x plus 1 by the denominator x plus 2. When we divide 2x squared by x, we get 2x. We multiply 2x by the denominator to get 2x squared plus 4x and subtract it. We bring down the next term plus 1 to get x plus 1. Now we divide x by x, which gives us 1. We multiply 1 by the denominator to get x plus 2 and subtract it. This leaves us with a remainder of negative 1. Our result is a quotient of 2x plus 1 and a remainder of negative 1. The end behavior is determined by the quotient. As the absolute value of x gets very large, the remainder term, negative 1 over the quantity x plus 2, approaches 0. This is the exact behavior of our first case. Therefore, the end behavior of h of x is the same as the line y equals 2x plus 1. This line is our slant asymptote. The function's graph will follow this line as x heads to infinity. Let's quickly summarize what we've learned in a table, just like the one in your notes. We can categorize all rational function n behaviors based on a simple comparison of degrees, n versus m. If n is greater than m, the function behaves like a polynomial quotient, which could be a slant asymptote. If n equals m, the function approaches a constant, and its asymptote is a horizontal line at y equals a sub n over b sub m. Finally, if n is less than m, the function approaches 0, and its asymptote is the x-axis, the line y equals 0. This table is an excellent tool for quickly determining the end behavior of any rational function without even having to graph it. Let's work through one more quick example to make sure everything is clear. Let's find the end behavior and any horizontal or slant asymptotes for k of x equals the quantity 6x squared minus 5x plus 2, divided by the quantity 3x cubed plus 7. The degree of the numerator n is 2. The degree of the denominator m is 3. In this case, n is less than m. Looking at our summary table, this falls into the third category. When the denominator's degree is larger, the function's value gets closer and closer to 0 as x gets very large or very small. Therefore, the end behavior is that k of x approaches 0. This corresponds to a horizontal asymptote at the line y equals 0, which is just the x-axis. Let's recap our learning objectives for this video. We started by defining a rational function as a polynomial over another polynomial. We then discovered that a rational function's end behavior, what happens to its graph at the far ends, is completely determined by comparing the degrees of its leading terms. Depending on whether the numerator's degree is less than, equal to, or greater than the denominator's, we found that the function would have a horizontal asymptote at y equals 0, a horizontal asymptote at the ratio of leading coefficients, or potentially a slant asymptote found through polynomial long division. These powerful techniques allow you to sketch the general shape of any rational function, especially its behavior as x goes to infinity, without needing a calculator. Keep practicing these 3 cases and you'll be a pro in no time. Thank you for watching.